I want you to imagine a machine that simply cannot break.
Right, a truly indestructible device.
Yeah, and I don't just mean something that survives a drop on the pavement or being dropped in water.
No, we're talking way beyond that.
Exactly. I mean a circuit so robust, so fundamentally unshakable, that it could sit inside the crushing, churning magnetic heart of a sun and just keep ticking.
It sounds like science fiction, honestly.
It really does. But welcome to the deep dive. Today, we are exploring a strange new material that is actively rewriting the rules of physics.
It's called uranium ditelluride, or UT2.
Yeah, UT2.
Yeah.
And going through our sources for this deep dive, it's pretty clear this isn't just some small incremental update to material science. It's a complete paradigm shift.
Oh, absolutely. I mean, as a quantum physicist, I can tell you that materials behaving like UT2 simply shouldn't exist. Not according to the classic foundational rules we were all taught in school anyway.
Because normally magnets are like the enemy of this kind of tech, right?
Yeah. Exactly. For roughly a century, we've known that powerful magnetic fields are essentially the super killers of high-end electronics. They just destroy efficiency.
But UT2 is different.
Very different. As we'll explore, UT2 treats the strongest magnets in the universe not as a threat, but almost as a structural reinforcement.
Which is wild. And by doing that, it holds the potential to solve two of humanity's biggest, most frustrating technological hurdles.
Right, mastering nuclear fusion and building a stable quantum computer.
But okay, before we get into those massive applications, I have to ask the question that I know you listening are probably screaming at your device right now.
I think I know what it is.
It's right there in the name, right? Uranium Ditelluride. The word uranium carries a whole lot of baggage.
It definitely does.
So are we talking about building future laptops and power grids out of something highly radioactive? Like, is this actually safe?
That is the perfect place to start because, well, it's a very natural reaction to that word. The short answer is yes, it is safe in the context we are talking about.
Phew.
Yeah, the uranium used in UT2 is depleted. It's essentially the same highly stable, low radioactivity material you might find used as counterweights in airplane wings or radiation shielding in medical devices.
Right, so you wouldn't want to grind it up and sprinkle it on your cereal.
Definitely do not eat it. But sitting in a sealed microscopic circuit inside a quantum lab or deep inside a fusion reactor, it poses absolutely no ambient danger.
Good to know.
Plus, the magic of this material isn't about radioactivity anyway. It's entirely about its structural geometry and how it conducts electricity.
Okay, that is a huge relief. So let's unpack that electrical behavior because to understand why this UT2 material is such a miraculous discovery, we really have to establish a baseline.
Right, we need to talk about standard electricity.
Exactly.
Yeah.
We need to look at why our current electrical systems are, for lack of a better word, dumb.
Dumb is highly accurate, actually. Let's look at standard electricity, the kind powering the device you're using to listen to us right now.
The normal stuff.
Yeah. In standard metal conductors, like copper wire, electrons act like a chaotic, panicking crowd trying to exit a stadium.
Oh, I like that visual.
They are constantly bumping into the copper atoms, ricocheting off each other, and generally bouncing around in zigzags as they try to move forward through the wire.
And all those physical collisions create friction, right?
Exactly. All that bumping around creates friction.
Right.
And what does friction manifest as?
Heat, which is exactly why my laptop sounds like a jet engine and burns my legs when I have 40 browser tabs open.
Exactly. It's just wasted energy. A huge percentage of the electricity we generate globally is lost, just pushing electrons through wires against that natural resistance.
So what's the fix?
Well, the solution to that inefficiency, which we discovered over a century ago, is the superconductor.
Right, superconductors.
Superconductors fix the heat problem by completely changing the behavior of the electrons. When you cool certain materials down to near absolute zero, the electrons stop acting like a panicked crowd.
They calm down.
More than that, they partner up. They form what we call Cooper pairs.
Oh, so they form a buddy system.
A quantum buddy system, yeah. And when they pair up like this, they synchronize. They stop bumping into the atomic lattice.
So no more stadium crowd.
Right. They coordinate and glide through the material, creating this magical, resistance-free flow of electricity, zero friction, zero heat, zero wasted energy.
That sounds absolutely perfect. But I know enough about physics to know there's always a catch.
Oh, there is a massive frustrating catch.
I knew it.
To form these Cooper pairs, the two electrons need to have opposite magnetic spins.
Opposite spins, okay.
Yeah, one electron is essentially spinning up and the other is spinning down. In the bizarre world of quantum mechanics, that opposite spin allows them to balance each other out.
So they can occupy the same relative space without violating the laws of physics.
Exactly. That opposite alignment is the delicate glue holding the pair together.
Okay, I think I see where the superkiller comes in. The magnets.
You got it. If you introduce a strong magnetic field to this delicate system, the magnet acts like an absolute tyrant.
Because a magnetic field wants everything to align with it.
Yes. So it forces both of those electrons to flip and point in the exact same direction.
And since they both suddenly have the same spin, that fragile quantum glue dissolves.
It instantly snaps apart. The superconductivity dies on the spot, and your magical zero-friction wire instantly turns back into a normal, highly resistive, heat-generating wire.
Wow. Just like that.
Just like that. This is the fatal flaw of 99% of all known superconductors.
Which is why we don't have hover trains everywhere.
Exactly. To levitate a massive commercial train, you need incredibly powerful magnets. But those very same magnetic fields destroy the superconducting circuits required to generate the lift in the first place.
They are fundamentally at war with each other.
Exactly.
So if I'm trying to picture this dynamically, it's like the electrons are two ice skaters doing this perfectly balanced, mirrored routine.
Oh, that's a good way to look at it.
Right. One leans far to the left, the other leans far to the right, and their opposing momentum is what keeps them locked together, spinning flawlessly across the ice.
Right. Right.
But a giant magnetic field is like a sudden gale force wind sweeping across the rink.
Which forces both skaters to lean in the exact same direction.
Yes. The balance is ruined, they let go of each other, and the entire routine just falls apart.
That is a phenomenal analogy. The magnetic wind obliterates the choreography. And for decades, physics largely accepted that as a hard boundary of nature.
Like, you want superconductors? Great. Keep them away from strong magnets. End of story.
Exactly. But then we found UT2.
The rebel.
The rebel material. UT2 completely ignores that rule because it fundamentally changes the nature of the electron dance from the very beginning.
Right. Our sources call this the spin triplet rebellion. What exactly is a spin triplet?
Well, UT2 belongs to an ultra-rare class of materials called spin triplet superconductors. In this strange material, the electrons in the Cooper pairs aren't opposites.
Wait, really?
Yeah, they don't have that up-down dynamic. They naturally pair up with parallel spins. They are already pointing in the same direction.
Wait, I thought you just said they had to be opposites to pair up without violating quantum rules.
In traditional superconductors, yes. And that's why UT2 is so mind-bending. Because of the unique, heavy atomic structure of uranium and tellurium, the electrons are able to lock into this highly unusual parallel state.
So they share a completely different kind of quantum relationship.
Exactly.
So because they are already parallel, when that gale force magnetic wind blows across the ice rink, they don't get blown apart.
Exactly. Instead of fighting the magnetic field, UT2 leans right into it.
Huh.
Think of a team of rowers who are already perfectly synchronized, pulling their oars in the exact direction the current is flowing.
So hitting them with a massive magnetic field doesn't snap the pairs apart.
No, the magnetic field actually reinforces their parallel state. It locks them in tighter.
That is incredibly elegant. But our sources mention that researchers didn't just test this with, like, a fridge magnet. They put it through a 60 Tesla stress test.
They did.
And I feel like we need to give some context for that number because just reading the figure 60 Tesla makes my eyes water.
The scale is almost incomprehensible. To put it in perspective, the Earth's own magnetic field, the one that stretches out into space and protects us from solar wind, is roughly 50 microteslas.
Okay, 50 microteslas.
Right. Now, a standard MRI machine at a hospital, which has a magnet so strong it can rip an oxygen tank across a room, operates at maybe 1.5 to 3 Tesla.
Okay, so 60 Teslas.
It is tens of thousands of times stronger than the Earth's magnetic field.
That's terrifying.
It is. If you subjected everyday materials to a continuous 60 Tesla field, their very atomic structures would begin to warp. The electron orbits around the atoms would physically deform.
Just from the magnetic force.
Yeah. Some theoretical physics models suggest magnetic forces in that realm could literally liquefy a human body by distorting the water molecules and disrupting the electrical signals in your nervous system.
Wow. It is an environment of supreme violence.
Supreme violence.
And they put a tiny piece of UT2 into that violence. What happened?
It didn't even flinch. It stayed superconducting.
That's crazy.
Right. It stared down a force that should break the fundamental laws of chemical bonds, and it just kept moving electricity with zero resistance.
That is just, it's difficult to wrap your head around. But what I find really fascinating is where the researchers take this next.
Yeah, the applications.
Because surviving a 60 Tesla magnet isn't just a brute force party trick. They immediately pivot from this raw, massive durability to applying it to the most fragile, microscopic technology on Earth.
Quantum computing.
Exactly.
And it makes perfect sense when you understand the roadblock quantum computing is currently facing. We hear about them all the time in the news.
Right, using qubits to perform calculations that would take a normal supercomputer millions of years.
But there's a reason you don't have a quantum computer on your desk yet. Qubits suffer from the noise problem.
Right, physicists call this decoherence. I've always struggled with this concept. Why is a qubit so fragile compared to the microchip in my phone?
Well, a normal computer bit is a physical switch. It's either a solid 1 or a solid 0. It takes a lot of energy to physically flip it.
Okay.
A qubit, however, exists in a delicate state of probability. It's essentially hovering between 1 and 0 at the same time.
Like balancing a coin on its edge.
Exactly. It's balancing on a razor's edge. Because of that, qubits are so incredibly sensitive that if a stray radio wave from a passing cell phone, or a cosmic ray from space, or even a tiny fraction of a degree of heat hits them,
The quantum state collapses.
yes, the calculation completely fails. It's like trying to build a 50-story house of cards on a table, and someone in the next room shuts a door too hard.
The vibration brings the whole thing down. So how does UT2 protect the house of cards? Our sources refer to it as a topological superconductor. What does topology have to do with protecting information?
So topology is a branch of mathematics that deals with properties that are preserved through deformation.
Okay, like what?
The classic example is a coffee mug and a donut. Topologically, they're the same shape because they both have exactly one hole. You could mathematically mold a donut into a coffee mug without tearing the dough.
Okay, I follow the geometry part.
Right.
But how does that apply to electricity in UT2?
In a topological superconductor, the flow of electricity is dictated by the fundamental geometry of the material's atomic lattice.
Okay.
The current doesn't just push its way through the middle of the wire like water sloshing through a pipe. Instead, the superconducting state is forced to the outermost edges of the material. It becomes locked to the surface.
Oh, interesting. So it's kind of like an electrical highway where cars can only drive on the absolute edge of the road,
Yeah.
but the road itself is carved into the indestructible geometry of the universe.
Exactly. Because the path is defined by topology, the entire global shape of the crystal, a localized disturbance doesn't matter.
Because it's not a local rule, it's a global rule.
Right. If a stray radio wave or a burst of heat hits one tiny section of the UT2, it can't derail the electricity because the electricity is following a rule set by the entire macrostructure of the material.
That makes sense.
You can't untie a knot in a piece of string just by flicking the string. You'd have to physically break the entire crystal to stop the flow. The information traveling along that edge is geometrically protected.
That completely reframes the fragility problem.
Yeah.
And the sources also mention this topological state opening the door to something called Majorana fermions. What are those?
Majorana fermions are theoretical particles that act as their own antiparticle.
Which means?
Well, in the context of our UT2 highway, they act as an automatic quantum memory backup. Imagine a single piece of delicate quantum data being split in half, and those two halves travel simultaneously along opposite edges of our indestructible highway.
Okay, two halves on opposite sides.
If some kind of random noise manages to hit one edge and corrupts half the data, the whole calculation isn't lost.
No, because the other half is safe.
Exactly. The other half on the far edge perfectly preserves the truth of the quantum state.
Because the local noise couldn't hit both opposite edges at the exact same time.
Precisely. The system can reconstruct the corrupted data using the protected half. It makes the quantum computer essentially self-healing and crash-proof.
That is mind-blowing.
It really is. UT2 could be the foundation that finally takes quantum computing out of these freezing, isolated, multi-million-dollar laboratories and puts it into practical, everyday use.
Okay, so we've established that UT2 can act as an indestructible bodyguard for the tiniest, most fragile data in existence.
Right.
But let's follow the thread of causality here. If this material is so fundamentally unshakable, why are we only talking about microscopic quantum processors?
Oh, we aren't.
Right. Can we scale this up? Can we use this indestructible property for something brute force, like macro power generation?
We absolutely can. And that takes us to the most massive energy challenge on Earth: nuclear fusion.
Holy grail.
Yeah. Fusion is the exact process that powers the sun smashing atoms together to release vast amounts of energy. If we can master it, we unlock clean, perfectly safe, effectively infinite energy for the entire planet.
But to do that here on Earth, we have to trap a literal burning star inside a bottle.
And obviously, you can't build a physical bottle out of glass or steel or titanium.
Right, the plasma is millions of degrees. Any physical material would instantly vaporize the moment the star touched it.
Exactly. So we build a bottle made out of invisible magnetic fields. We use colossal machines called tokamaks.
Those are big donut-shaped ones, right?
Right. Giant donuts surrounded by massive superconducting electromagnets. These magnets generate a field so intensely strong that it squeezes the burning plasma and suspends it in a vacuum, never allowing it to touch the walls of the machine.
That is amazing engineering.
It is, but this is where the grand, frustrating irony of fusion comes into play.
Let me guess. The magnet problem comes back to haunt us.
It does, with a vengeance. To hold a denser, hotter plasma and generate more power, the magnets have to be intensely powerful.
Right.
But remember what we established about normal superconductors. Powerful magnets destroy them by snapping the Cooper pairs.
Oh, wow.
So the very magnetic field required to hold the star is constantly threatening to destroy the superconducting wires that are generating the field in the first place.
It's a literal catch-22. The harder you squeeze the plasma, the more likely you are to break your own machine.
Exactly. And if the magnetic field gets just a fraction too strong, the superconducting wire suddenly fails. It loses its zero friction state.
And what happens then?
In a millisecond, all that massive electrical current hits intense resistance.
Which creates heat.
A catastrophic spike in heat. The system experiences what we call a quench.
A quench? That doesn't sound good.
It isn't. The liquid helium cooling the wires instantly boils away, the magnetic bottle shatters, the plasma expands and hits the walls, and the fusion reaction essentially blows itself out, shutting down the reactor.
That sounds like an expensive mistake.
Very. We currently spend billions of dollars building these stadium-sized fusion reactors just to carefully tiptoe around this quenching problem. We're always trying to balance the magnetic force against the fragility of the wires.
But if we build the electromagnets out of UT2, the catch-22 just vanishes.
Yes.
Because UT2 doesn't quench, it loves the magnetic field.
It thrives on it. That is the paradigm shift. If you have an indestructible circuit, you don't need a reactor the size of a football stadium to carefully manage the heat and the delicate magnetic balance.
You can just crank it up.
Yeah, you can push the magnetic field 10 times higher without fear of quenching. The mathematical models in these sources suggest that with UT2, fusion reactors could shrink from the size of a sports arena down to the size of a commercial delivery truck.
Wait, really? A star in a magnetic bottle, sitting in a warehouse, safely powering an entire city grid forever.
Yes, a localized, perfectly safe, infinite energy grid without the constant fear that the containment field will blow out its own power source.
That sounds like pure science fiction.
I know, but the physics is sitting right there in the laboratory.
Okay, that alone is enough to change human history.
Yeah.
But as I read through the final sections of our sources, just when I thought I had a handle on how this material works.
You saw the reentrant part?
Yeah. Just when I thought, okay, it's a super tough wire that likes magnets, UT2 does something that apparently leaves physicists completely baffled.
It does.
It involves a concept called reentrant superconductivity. What is happening here?
This is the part of the research that genuinely gives physicists chills because it challenges our fundamental understanding of thermodynamics.
Okay, walk me through it.
So let's go back to that 60 Tesla stress test. As we established, UT2 survives fields that would warp normal matter. But even a rebel has limits.
Right, infinite durability doesn't exist. So what happens when they push it past the limit?
Well, the researchers took the UT2 and they kept cranking the magnetic field higher and higher. 65 Tesla, 70 Tesla. And eventually, the superconductivity did die.
Okay.
The Cooper pairs broke. The resistance came back. The material became normal again.
Which makes total sense. Going back to our analogy, the gale force wind finally got so strong it just blew the synchronized rowers out of the boat entirely.
Exactly. But the researchers didn't turn the machine off.
Why not?
Curiosity, mostly. They decided to keep cranking the magnetic field even higher, deep into the zone where superconductivity was supposedly dead. And suddenly, at an even more extreme magnetic intensity, the superconductivity sprang back to life.
Wait, I'm struggling to understand the mechanism there. How can adding more destructive force bring it back?
It's weird, right?
Yeah, if heat melts ice into water, applying more heat doesn't turn the water back into ice.
That is a brilliant way to frame it, actually, because it involves something similar, a phase shift.
A phase shift.
Yeah. The current prevailing theory is that the extreme hostile environment of the ultra-high magnetic field forced the electrons to reorganize. The original spin triplet pairs were destroyed, yes, but the overwhelming magnetic energy actually restructured the Fermi surface of the material.
The Fermi surface. What does that mean for the electrons?
It essentially changes the allowed energy states for the electrons.
So the environment itself forced a new reality.
Precisely. The intense magnetic field forced the electrons to lock into a completely new, exotic configuration that can only exist inside that extreme pressure.
Oh, wow.
It's almost like discovering a weird, impossible kind of ice that only freezes when you expose it to a blowtorch.
That is wild.
We are witnessing a state of matter adapting in real time to an impossible environment, inventing a new physical state just to survive.
It's staggeringly beautiful. When you synthesize all of this, from protecting delicate quantum data to holding a fusion star in a bottle to literally reinventing itself under pressure, we are looking at the foundation of a completely new technological era.
We really are.
If we commercialize UT2, the fundamental barrier of overheating in extreme environments just ceases to exist.
The practical applications will touch every field. Think about the medical industry.
Oh, like MRIs?
Yeah. Right now, MRI machines require massive, highly expensive liquid helium cooling systems just to keep their fragile, superconducting magnets from quenching.
Which is why MRI scans are so expensive and localized to massive hospitals.
Exactly. With UT2, those magnets could be smaller, vastly stronger, and operate without the fear of the field destroying the circuit. We're talking about MRI machines shrinking to the size of a smartphone.
Wait, a smartphone?
Yeah. You could have hospital-grade deep tissue imaging in a handheld device used by first responders in the field.
And it changes how we look at the stars, too. Space exploration is limited by the destruction of electronics.
Space is very harsh.
Right, but if we have magnetic shields that never fail, we could build spacecraft capable of safely sailing right through the intense, highly destructive radiation belts of Jupiter.
We could.
We could send probes into the most hostile environments in our solar system, knowing our electronics are practically invincible.
And that actually brings us to the ultimate mind-bending implication raised at the very end of our sources.
Well, what's that?
We know UT2 can survive a 60 Tesla field.
Huh.
We know it has this bizarre re-entrant property where the superconductivity comes back to life, stronger and adapted at even higher fields.
Right.
So what happens if we discover a material that can survive 600 Tesla or 6,000 Tesla?
Where in nature do you even find a magnetic field that intense?
You have to look far out into the deep cosmos. The most extreme magnetic fields in the universe exist around spinning neutron stars, the incredibly dense remnants of collapsed suns.
Okay.
The magnetic fields there are billions of times stronger than anything on Earth. Some astrophysicists are now hypothesizing that in these unimaginably intense environments, matter itself might undergo this exact same re-entrant transition.
You mean the star itself?
The entire outer crust of a neutron star, under that crushing magnetic force, might actually lock into a permanent state of zero electrical resistance.
Wow.
It might become a giant, perfect superconductor.
So if that is true, then the universe isn't just full of isolated burning stars in a void.
Exactly. It implies that these stellar bodies might be generating macroscopic quantum states. The extreme universe itself might operate as one giant, interconnected electrical circuit.
A cosmic-scale quantum engine.
And down here on Earth, inside a tiny little crystal of uranium ditelluride, humanity just found the very first piece of the wire.
That is incredible to think about. It forces us to ask the ultimate question. If we now have the blueprint for a machine that thrives inside the crushing magnetic heart of a star, what will we do when the power never stops?